Here we are at the penultimate lecture in this course. We've managed to cover a very great deal, and I hope by now you've got a sense of what an amazingly rich story cosmology is telling us. The progress recently has been quite remarkable, and it's come in two rather different ways. On the one hand, several huge observational projects have produced superb datasets, and on the other hand, these datasets have been interpreted and understood using detailed theoretical calculations, often using huge computer simulations. So the subject right now is in an extremely interesting condition. The primary story has been established. Essentially, it's the inflationary hot Big Bang story that I've tried to tell in these lectures. But as always in science, when the first set of questions is answered, another set of questions arises. So in this lecture, my aim is to highlight some of the next steps for cosmology. What are cosmologists currently working on? And what might they learn by, say, 2030? Now, I've picked out 6 themes to look at, and although they don't cover all the work that's going on, I think they'll give you a good feel for the near future of the subject. And I'm also hoping, of course, that as I move from one theme to another, in effect, I'll be reviewing much of the material we've covered in the course. So let's start off with our first theme, dark matter. And I've picked 2 areas: efforts to detect dark matter particles and efforts to map its web-like distribution. So, arguably, the most fundamental discovery in all of science at the present time would be to actually detect dark matter particles. One of the approaches is to use particle accelerators to actually create dark matter particles in high-energy collisions. And the other approach is to detect cosmic dark matter particles using extremely sensitive detectors buried deep underground. Now, the discovery of dark matter particles has Nobel Prize written all over it. First, you'd be discovering the primary matter component of the universe, and second, you'd be taking physics beyond the standard model. So it would be a simultaneous breakthrough in cosmology as well as fundamental physics. What about future astronomical observations of dark matter? One of the primary projects is to use gravitational lensing to map out the web-like pattern of dark matter and watch its structure grow over time. The idea is that the light from very distant galaxies gets slightly distorted by the gravity of dark matter. It's a bit like looking through an old pane of uneven glass. Everything looks a little wonky. So by taking deep images and analysing the shapes of hundreds of thousands of distant galaxies, it's actually possible to reconstruct the distribution of dark matter along the path. Here are some of the first results of this method, using the Hubble telescope to look at a small patch of sky about twice the size of the full moon. It shows the dark matter and even reveals how it changes from being smoother far away, long ago, to being more clumpy nearby, today. This weak lensing technique, as it's called, is really remarkable in that it renders visible something that is otherwise inherently invisible. So for the future, there are several projects that are going to use this technique to map out dark matter. But I'll just mention 2 of them that will actually do much more than that. They're the Pan-STARRS project with 4 1.8-metre telescopes and the Large Synoptic Survey Telescope, LSST, with a single 8.4-metre telescope. As you can see, the Pan-STARRS project is underway, while the LSST is still in its design stages. Both projects aim to photograph large areas of the sky using huge cameras with specially designed optics. I think one of the most remarkable things to come from these projects will be the positions and approximate distances and properties of almost 1 billion galaxies, as far away as 11 billion light years. That's much bigger than the recent Sloan or 2DF redshift surveys I've shown you in the previous lectures, and extends almost to the edge of the visible universe. So this situation is similar to 18th century global exploration, when most but not quite all of the world had been mapped. And just like on Earth, once it's complete, that's it. There are no more continents to find. There's no more volume in which to find galaxies. Within 1 century, we will have gone from knowing just our galaxy to knowing all galaxies. Now, our second theme is dark energy. By now, the evidence for dark energy is pretty strong, and we know it makes up about 73% of the total cosmic density. But we still have no clear idea what it actually is. So finding that out is the next major goal. Remember, dark energy is thought to be one of the following: a simple, constant vacuum energy, which behaves like Einstein's original cosmological constant; quintessence, which is basically a vacuum energy that varies with time; or a new and unknown property of gravity, something that's beyond Einstein's theory of general relativity. So the major task now is to try to sort out which of these three it is. And you won't be surprised to hear that the way to do this is to see whether the density of dark energy changes over time. And in cosmology, that always means you look far away, back in time, to see if it was different back then. And there are actually 3 different approaches for doing this. The first is to simply improve on the original method for discovering dark energy, using distant supernovae to measure how the expansion rate has changed over time. There are already several projects using ground-based telescopes to gather more supernova data, but a huge leap forward would come from a dedicated telescope in space, like this one, called SNAP, for Supernova Acceleration Probe. Just to give you an idea of the kind of improvements, here's the classic diagram from 2003, showing how more distant supernovae, that's along the x-axis, get fainter up the y-axis. The data nicely distinguish between universes with and without dark energy, but they can't go much beyond that. Look how the situation would improve with 2,500 new supernovae from the SNAP telescope. The expansion rate is really nailed across 9 billion years of cosmic history, which would tell us quite accurately whether or not the density of dark energy has changed over time. The second approach uses the technique I mentioned a minute ago, weak lensing, to study how the clumpiness of dark matter changes over time. This computer simulation shows how the dark matter changes from being very smooth 12 billion light years away to being quite lumpy nearby. It grows clumpier over time as gravity pulls it into denser regions. But remember from lecture 22, the accelerating expansion caused by dark energy tends to suppress the growth of clumping. So if you measure how clumping changes over time, then you can infer how dark energy changes over time. So that's the second method. Now the third method measures what are called baryon acoustic oscillations. This method makes use of the acoustic waves that we see as the patchiness of the microwave background. Remember, the sound spectrum of that patchiness gives this amazing graph with its fundamental and harmonics. But of course, the gas that makes those patches goes on to make galaxies. So the harmonic peaks on the microwave background should be present in the patterns of today's galaxies. And as we saw in lecture 22, although your eye can't pick them out in the galaxy pattern, the roughness spectrum shows them as these little wiggles. Now these little wiggles are extremely useful for the simple reason that we know their true physical size, because we understand the physics of how they were made in the young universe. So, just as the faintness of supernovae allows us to measure distance because they act like standard candles, so the angular size of the acoustic harmonics also allows us to measure distance because they act like standard rulers. And this gives us another way to measure how the expansion rate changes over time, and so whether dark energy changes over time. But the real power of these three methods comes in combining them. Here's a diagram with omega matter along the x-axis and W up the y-axis. Now remember from lecture 26, W is the main parameter that measures whether dark energy is changing or not. Look at how the data from the supernovae and the baryon acoustic oscillations combine beautifully to single out this little region, suggesting W is roughly -1. This is the value we expect for a constant vacuum energy. But to properly distinguish between the various options for dark energy, one really needs much better data, which of course is what these major projects are designed to do. Now, our third theme is to really begin to observe properly the first billion years. The primary goal is to study the first stars and galaxies. And a second goal is to observe the diffuse gas that's condensing to form both of these, which I'll come back to in a minute. So here from lecture 18 is our first billion-year timeline. The Big Bang and microwave background are the narrow line on the left, after which there is a 200 million year period of darkness before the first stars begin to form. And after another few 100 million years, the first infant galaxies form. It's an absolutely crucial time in the cosmological story, and yet it still remains almost completely unobserved. Remember from lecture 19, the Hubble telescope's ultra-deep field only just manages to see galaxies at the end of the first billion years. What's desperately needed are bigger telescopes, both in space and on the ground. So let's look at what the next couple of decades will bring. The successor to the Hubble Space Telescope is the James Webb Space Telescope, and it's due to be launched in 2013. It's named after the man who made sure in the 1960s that science was one of NASA's primary missions. It has a compound mirror that's 6.5 meters across, much bigger than Hubble's 2.4 meter mirror. The whole telescope is carefully folded up and launched in a European rocket and taken to a special parking spot about 4 times further than the Moon on the opposite side to the Sun. Once there, it slowly unfolds to make this rather bare-looking structure with large sheets to protect it from the sunlight. Here's a simulation of what the telescope will see in a small patch of sky. It's an absolutely amazing vision of galaxies upon galaxies upon galaxies, near and far, down a 13 billion light-year tunnel. Many of those tiniest dots will be infant galaxies in the first billion years, and a few will be the first stars. It'll be a really wonderful moment when, for the first time, we see the universe's first stars. Now, along with this space telescope, cosmology is also benefiting enormously from a new generation of huge optical telescopes on the ground. Here are a few examples: the famous Keck telescopes in Hawaii. Here are 4 European-run telescopes in Chile. The Large Binocular Telescope in Arizona. And the Gemini North Telescope, also in Hawaii. The main feature of all these telescopes, of course, is having a huge light-gathering mirror. Here's one 8 meters across. That's a person standing in the middle. A mirror of this size gathers 4 million times more light than your eyes, and the cameras are 50 times more sensitive than your retina. So combined, you can see how telescopes like this could easily pick out a candle on the moon, which is what they need to do, because that's about how faint the first galaxies are. Of course, the next generation of telescopes, like the one illustrated here, will have 30-metre mirrors and are planned to start around 2015. All these new optical telescopes are a wonderful example of how modern technology really drives science forwards. So let's look at another example, this time for radio telescopes. So here's our first billion-year timeline again, and this time let's think about the diffuse gas that's making those stars and galaxies. Remember, the microwave background, way over on the left, is when the universe changes from an ionized gas to an atomic gas. The electrons get caught by the nuclei. So throughout the dark age, the universe contains just cooling atomic hydrogen and helium gas, getting clumpier and clumpier until finally, after about 200 million years, the first stars form. Now remember, these stars are hot and bright, and their ultraviolet light begins to re-ionize the gas. The energetic photons smash the atoms and knock off the electrons. So there's an extended period, from about 200 to 800 million years, called the epoch of re-ionization, as the atomic hydrogen gradually gets more and more ionized. Here's a computer simulation of this period. You can see how we start with mostly neutral gas in orange, and then where stars form, the ionized regions gradually spread out wider and wider, until the entire region is almost completely ionized. It's a very important time to study, because the patterns of ionized and atomic gas tell us a huge amount about the nature of those first stars and galaxies. So a major goal for the next 2 decades is to observe this whole period. But how do you do that? Well, you may remember from Lecture 9 that simple atomic hydrogen gas has the enormously useful property of emitting radio waves with wavelength 21 centimetres, that's about 8 inches, which now in the current context is redshifted to between 1 and a few meters wavelength. So what we need are radio telescopes specially sensitive to these very long radio waves. Now, once again, although there are many projects to do this, I'll mention just the 2 largest ones. The first is already being built. It's called LOFAR, for Low Frequency Array. And it's the first of a completely new kind of radio telescope. Each antenna is remarkably simple and receives radio waves from all over the sky. But there are thousands of these, spread across northern Europe, with a concentration in Holland. The signals are sent to a supercomputer housed in this building, where they are combined in extremely sophisticated ways. And the upshot is that the entire array acts like a single telescope that can study any part of the sky with great sensitivity. Actually, a much bigger version of this is planned to begin around 2012, and it's called the Square Kilometre Array, or SKA. And like LOFAR, it has a central region with more antennae and outlying stations spanning a few hundred kilometres. The total collecting area is 1 square kilometre, giving it extraordinary sensitivity. So with these and similar instruments, perhaps in 10 or 20 years, I'll be able to show you pictures of hydrogen filaments in the dark ages, gathering, ready to make the first stars. Back to our human metaphor that maps all of cosmic history onto a human lifespan, this is equivalent to studying the gestation period, just using ultrasound to watch the embryo's development prior to birth. Now, theme 4 is galaxy evolution, And of the many planned projects, I've picked two that I think are particularly interesting. One uses a new facility to find and study infant galaxies, and the other detects the merging of massive black holes. So remember from lecture 19 that the early universe is filled with colliding and merging galaxies, a bit like these lovely nearby examples. And during these collisions, many new stars are born. So you may be surprised to see that the spectrum of a typical merging galaxy looks like this. It goes all the way from ultraviolet on the left, through optical and infrared, to radio on the right. Notice that the starlight in the optical is a minor component compared to this huge bump in the infrared. What makes all that infrared light turns out to be tiny carbon and silicon particles that astronomers call dust. They absorb most of the starlight and re-radiate it in the infrared. So obviously, if you want to see extremely distant colliding galaxies, you should forget about starlight and focus on this big bump. Now, in distant galaxies, the spectrum is red-shifted, which moves that bump from the infrared over into this part of the spectrum, right on the boundary between infrared and radio, with about 1 millimeter wavelength. Well, for this and other reasons, in 2012, this spectral region will be revolutionized by a fabulous new instrument called ALMA, for Atacama Large Millimeter Array. It has 64 dishes like this one, spread over a few kilometers, and it's located way up in the high Atacama Desert in Chile. This new facility will add to all areas of astronomy, but in the current context, it'll really allow cosmologists to study in detail those chaotic early times, when the first galaxies were rapidly growing by mergers and starbirth. Rates were at an all-time high. Now, you may remember from lecture 21 that these early wild times were also when black holes were first formed. And although they do this and how they do this, we still don't really know, it is thought that black holes grow in two different ways: by pulling in and swallowing gas and stars, and by merging. Two black holes can merge to make a bigger black hole. Just watch this simulation of the late stages of two merging galaxies. See how quickly their central regions merge together. Now, if those central regions each contained a black hole, you can see how the black holes themselves might also merge. Now, when two black holes finally spiral in together and merge, it's thought that a lot of their mass is converted into gravitational waves that move out into the universe at the speed of light. So, billions of years later, when they cross the solar system, those gravitational waves shake everything a little bit. The shaking is extremely slight, but technology is now almost able to detect it. And that's the aim of the LISA project, which stands for Laser Interferometer Space Antenna. The project has 3 satellites, 5 million kilometers apart in a huge triangle. And the distance between the satellites is measured extremely accurately using laser beams. All 3 satellites orbit the Sun, trailing the Earth in its orbit. When a gravitational wave passes by, the triangle arms lengths change very slightly, about 1,000th of the diameter of an atom. And amazingly, this can actually be measured. And so the pattern of the gravity wave can be analysed, and from this, the nature of the black hole merger can be figured out. When it's operating, sometime in 2020, LISA is expected to be able to detect massive black holes merging anywhere in the visible universe, of which there might be roughly 1 occurring per year. This would be an extraordinary scientific achievement, partly because you're actually witnessing one of the most dramatic events in the universe, but one is also using an entirely new window on the universe, the gravitational wave window. Theme 5 is to try to find more evidence for inflation, and there are two key methods, both of which require very careful observations of the microwave background. With luck, these should be made by a European satellite launched in October 2008 called Planck, after Max Planck, who was one of the founders of quantum mechanics. Each decade, there's been a steady improvement in the quality of the all-sky microwave maps, from COBE in 1990 to WMAP in 2003, and now here's the predicted Planck map with even more sensitivity and detail. This higher quality detail should yield a better sound spectrum, and this in turn will allow a primordial spectrum created by inflation to be measured more accurately. You may remember from lecture 32 that the slight tilt and curvature in this spectrum not only provides evidence for inflation, but they also allow you to figure out some very important details of how inflation occurred, what the shape of the potential is, to use the proper term. But the most important quality that the Planck satellite is looking for is the polarization of the microwave background, the direction the microwaves wiggle when they get to us, as you can see in this illustration. Remember, inflation shakes all of space-time, and this sends out gravitational waves that leave a characteristic pattern on the polarization of the microwave background, a sort of spiral pattern. Now, detecting these polarization patterns would be viewed as extremely strong evidence for inflation, so it's a huge current priority in cosmology. Now, my final theme is the early universe, and drawing from lectures 28 and 29, I'm just going to list the outstanding questions that may or may not be answered in the next couple of decades. The first four questions concern the first picosecond. Why did matter have a slight 1 in a billion excess over antimatter? What are the properties of a quark-gluon plasma? Remember, that's the stuff the universe was made of before 10 microseconds, so it's pretty important to understand its behavior. Did the early universe obey supersymmetry? And if so, is the lightest supersymmetric particle also the dark matter particle? And finally, does the Higgs boson exist? And if it does, how does it give mass to all the other particles? All these four questions are within reach of our best current accelerators. For example, the new Large Hadron Collider at CERN has experiments that should shed light on all four of these questions. So who knows? Maybe in 10 years, at least some of these questions will be answered. But the next questions are well beyond any feasible experiments. They concern the much earlier time, when the Big Bang got its launch. So progress here is only likely to come through developments in theory. So we want to know how and when inflation occurred, and how long did it last for? And we also want to know the form of the inflaton potential. That's the hill down which the ball rolls. So obviously then, what we really need is a better understanding of the nature of inflation. But the greatest challenge is to place inflation into the wider context of the pre-inflation universe. And to do that, one needs a theory of quantum gravity. Among the various possibilities, string theory is thought to be the most promising. But it's also fiendishly difficult, and it may be many years, if ever, before this fundamental part of the cosmological story becomes clear. So I hope this lecture has left you feeling that cosmology is in an extremely healthy and interesting time. Although much of the basic story now seems to have fallen into place, there are nevertheless many wonderful puzzles remaining, including some fundamental ones. So as I mentioned at the beginning of the first lecture, now is a great time to be a cosmologist, or to simply find out about the subject.